This is a presentation of number 7959, and it's called Statistical Synthesis and Analysis of Optimal Direction Finding Algorithms. And all of the next three reports are going to be connected with Direction Finder. That's why I've combined them, and they have the same idea, and they are done according to one project, a project of young scientists that is sponsored by the Ministry of Education of Ukraine. And four of these authors are young scientists, and they are part of this project. And it's connected to it's connected to such system as Direction Finder. And these systems, they've got the new way of developing in 2022. Because of the war in Ukraine, I think that Ukrainians have seen it, and I see that, and I am sure that whole the world saw the developing of UAVs. UAVs are used every day, and not only in military section, but in for traveling, for mass media, for some other applications, so many areas. And because of necessary to control position of this aircraft, and because of a lot of situations when people lose their UAVs, it's necessary to develop systems for safe traveling and safe flying to the previous position of these UAVs. And to do it, it's necessary to develop some systems with beacons, and that aircraft can understand its position in space and can adjust onboard systems for traveling in the predefined location. And the most popular for this question, it's Direction Finders, and we started to do this project and started to analyze how to improve quality of Direction Finders and how to place them on UAVs and to improve their characteristics. And we were interested to make it in a compact way and to make it high quality and wide range of unambiguous measurements of angular positions. So Direction Finders have very wide applications. It's maritime and aircraft navigations, emergency aid, air defense, radio astronomy, and a lot of other applications. It's only just some of them. When we started to analyze these systems, we found that a lot of literature describes these methods like Direction Finders. They could be based on amplitude measurements, phase measurements, Doppler frequency measurements. They could be multi-antenna, two antenna, then wideband Direction Finders, and others. But we saw that mainly they are described on the base of engineer experience, on the base of many years many years application, and we did not find the good theoretical explanation about the structure of receiver, for example, the structure of signal processing algorithms. And to make something new to develop, we had to understand what are the main operations and what are the problems of the usual two antenna amplitude direction finder. That's why we decided to synthesize optimal algorithms, and to do this, we were using uh, well-known statistical theory of signal processing algorithms optimization, and particularly method of maximum likelihood method. And to understand the optimal algorithms, we presented the geometry of the measurements. So we have two antennas with two antenna patterns, and they are placed in space not in the same way, slightly in with some shift in the angle. And here we have theta s. It's the direction of our source that we have to measure and to understand the direction. And to specify the signals, we were using such a model of its convolution of uh, antenna pattern with position of our dot source of radiation. And we will predefine that we know the complex amplitude of the transmitted signal, and we know the central frequency of the transmitted signal. And using these two antennas with different position of main lobe, we will stated the observation equation that consists of received signals and internal noise. And then using the method of maximum of likelihood, we had to synthesize optimal algorithms. So we have formulated the problem. It's according to the criteria of the maximum of the likelihood function. It's necessary on the time interval for receiving the signal optimally process the observation equation and estimate the angular position of radio source. And to do this, we defined uh, um, uh, likelihood function, and then to find the optimal algorithm, we have to find maximum of this likelihood function. And to do this, we just have to find the uh, derivative of this likelihood function and equal it to 0. So in this case, we get a likelihood equation, then make a lot of calculations, some simplifications and other operation, and we got two possible algorithm of direction finding operation. The first one is well known. It's algorithm of power subtraction. So in this case, we have uh, every signal from our antenna in the receiver that take into account internal noise have to convolute with optimal pulse characteristics of the receiver, and this pulse characteristics is defined by um, envelope of the signal and central frequency. Then we have to calculate the subtraction of these powers, and this subtraction have to be divided into k. Uh, this is uh, the characteristic of discrimination characteristic of the direction finder, and energy of the received signal, and some central position of our direction finder. Theta 0 is the position when we have equal signals in every antenna. So, and the other one algorithm, it's power division algorithms. It's a um, uh, it has some advantages and disadvantages. Uh, Advantage is we can eliminate all the variations of amplitude in our antenna patterns, and all the variations in of signal, of transmitted signal, because of atmosphere, also because of some problems of signals, um, multiple transferring, and others. In this case, we can eliminate this problem using this division. But it's other type of algorithms also almost the same. Also, we can measure theta s. And to understand the limit errors of these algorithms, we have calculated marginal errors also from that likelihood functional. We can divide it, and we found that limit errors of angular measurements is inversely proportional to signal to noise ratio of the received signal, square of maximum of it's like antenna gain, square of antenna gain in this direction. And this is one I'm sorry, it's this is a slope of discrimination characteristic. And here on this slide, you can see the first example. It's we have two antenna patterns with relatively narrow beams, and the result of their subtraction is this function. And this function can be stated as a discrimination characteristic of direction finder. And its slope, it shows the quality of our possible measurement of direction. The higher this slope, the better, the lower limit errors of measurements. But in this case, we have other restriction. It calls the unambiguous measurements of the angle. And in this case, we make narrower this these limits of unambiguous measurement of the direction. And to increase this region, it's necessary to use wider antenna. But in this case, we have the other contradiction. The limit errors of corner measurements makes this situation worse. So in this case, we have to solve this contradiction, and using these results, you can develop algorithm, develop receiver, and calculate the possible limit errors of measurements. This is all that I did want to tell you about this report. Do you have any questions? Okay, then I can continue and show you the other two reports, and then we can discuss these results.